Now let's leverage the measure theory to measure the probability of an outcome, defining what a probability is and what are the distributions. So how can we describe in a rigorous way a random phenomenon? For example, the rolling of two dice. Well, rolling a dice is like this graph. We start on the left side with the face of a dice. This, through our mind, is transformed in a number, and then here the probability kicks in. We are able to count and to assign to each of these red numbers what are their probability. So in particular, in the previous slide here, we are taking one face of a dice and assign it to this yellow space. But we would also like, talking about probability, for example, to consider even more complex scenarios. For example, what if I want to consider the result that is less than 3? So I have the phase 1 and the phase 2, and this can be written as less than 3. Then we have the 3 condition, and then we have greater than 3, in which we assign the 4th, the 5th, and the 6th phases. And to these 3 elements of this orange space, we assign a probability: 1/3, 1/6, and 1/2. Now, this is exactly what a sigma algebra is. On the left side, omega will be called sample space, and each subset will be part of a bigger collection, the sigma algebra. In particular, let's wait a moment. On the right side, the green set, for now, will be called the range of probabilities. So, given a measurable space, we define a measure on it, the probability measure P, and omega, the sigma algebra on omega A, and the measure on the measurable space P will be our probability space, which is, of course, a measure space. So thus, let's refresh the previous slide and define what these elements in the collection of subsets of omega are. For example, here we have just one element of omega, which also stays inside the sigma algebra. Well, this is called an elementary event, also known as sample point, which is in practice a singleton. More complex events could be created. For example, here the greater than 3 becomes the dice faces 4, 5, and 6. This is a compound event because it requires a lot of singleton. It's a union of singleton. So the probability measure enjoys several properties. For example, in the first property, we already know that through the definition of measure, the measure of the empty space is equal to 0. But the probability measure is a finite measure, so the probability of omega is finite, is less than infinity, and in particular, in probability, we define the probability of omega as equal to 1. So since omega and the empty space are always in the sigma algebra, and thanks to the monotony of the measure, we can write these two properties. In the third property, instead, we rewrite the fact that the sigma algebra is closed under complementation, and we apply this property through the measure. So if we take, remember, this is an event now, where is a subset of the bigger collection, the sigma algebra, and now it's called event. So if we take the, of course we know we can compute the probability of this event, but since the measure is defined on a sigma algebra, and the sigma algebra is closed under complementation, the complementary event AC here is admitted, is inside the sigma algebra, so we can compute the probability of it, and we can show that the probability of the opposite event, the complementary event of A, is equal to 1 minus the probability of the event itself. So that's why we have defined the sigma algebra with this property, the fact that it's closed under complementation, because we already know what probability we would about the probability measure. With this third property, we can evaluate the probability of the opposite event, the complementary event. In the fourth property, we show again that the measure is monotone. In particular, we have two events, and one event is a subset of the other. Then, of course, the probability of the first event is less equal than the probability of the bigger one. The last property is particularly important, in which we have two events, and we want to compute the probability of the union of these two events. This means that we want that A or B to happen. And this can be written as the probability of A plus the probability of B minus the probability that an intersection between A and B, which means that happens A and B. So we will return to this definition, to this property. But this means that we can evaluate the probability that one or the other event will happen. In particular, this last term, the probability of A intersection to B, if is equal to 0, then means that the two events are said to be incompatible or mutually exclusive. This means that it is impossible for both to happen at the same time. It means that A and the probability of A and B is equal to 0. For example, it could be A could be there's a sun outside, the sun is shining, and B could be I take the umbrella. So the probability that is the sun is outside and I take the umbrella is equal to 0. They cannot happen at the same time. Then we have since the two events could be mutually exclusive, so this term is equal to 0, then if the two events are like that, the probability of A or B to happen is equal to the probability of A plus the probability of B. So this is a little slide as a reminder. When we write this, the union, it means A or B. We accept both. So this we consider what is around, inside the blue circle and inside the green circle. So it means that A or B could happen. It's the same. In the intersection between A and B, it means that the two events must realize at the same time. We are in the intersection here between the two sets. Now we can introduce the fact that if in a probability space we take two events and we say that these two are independent now, if the probability of this intersection, which means A and B to happen, is equal to the probability of A times now the probability of B. Independent means that one event has no effect on the other. In particular, with the independence in mind, we can introduce another concept, the conditional probability. And here the conditional probability can be written as the probability of A given B. What is the probability that A to happens if B happens? And is defined in this way: the probability of A and B divided by the probability of B, which is in the given here. But if the two events are independent, we can substitute this definition here at the numerator, and we get P of A. So it means that the probability of A conditioned by the event B given B is equal to P of A. Of course, they are independent, they are unrelated. They happen independently. So there is not conditioning between the two. So we have to take care to distinguish incompatible events and independent events. Incompatible events means that they cannot happen both at the same time. But still one event could be conditioned by the other. That happens maybe 1 second after the first one. In the independent events, it means that the two events have no effect on each other. Still, we can have independent events but compatible events. Two events happen at the same time, but they are not related to each other. So now I want to detail a little bit more about the sigma algebra in probability theory. So imagine playing a ring toss game with a friend. Here the sample space is omega, and is I missed the shot or I hit. Then omega represents the sure event, which means I miss or I hit here. The probability of happening at least one of the two is equal to 1. And the null event represents the impossible event, could not happen. I miss or I hit. So the probability is equal to 0. That's what we have seen so far. But there could be something else. Let's say that this friend is a funny guy, and after a few tries you discover that he rigged the game. The ring is smaller than the pole, not like in the picture. So the event it now, what we have said so far is true, but we can detail a little bit more about the probability of the event hit and the event miss. The event hit in particular still exists in omega, but now it cannot ever happen. We have discovered that will never happen since the game is rigged. So this is called negligible event. In fact, the probability of it is equal to 0. Its complementary event here, the miss, is then an almost sure event. In fact, the probability of miss now is equal to 1. So we have the same probability like we have seen, for example, here in the null event, the null set, and here with omega. But we are not considering the whole set, the whole collection of elements, and no element. We have two events that have their dignity, but that's why we don't use the sure events, but we say it's an almost sure events to distinguish between omega and the single event miss, and we talk about a negligible event instead of impossible event. So far we have described the omega, which is our sample space, and the range of probabilities. But we are missing what is in the middle, the intermediate step between the sample space and the range of probabilities. Now let's close this gap and define a particular measurable function, which we will call random variable. And this random variable goes from one element of the sample space to this particular orange space. This is a random variable. And the random variable, since it's a measurable function, inherits this property. Now, we can, since it is a measurable function in a measure space, we can compute the measure onto the random variable. How? But how? Remember that we have defined a measure in omega, our sample space. But the output of a random variable goes in this set, this orange set. So we have to describe, using the probability measure, the probability as something in the blue space. And to do so, we use this convention. The probability of x here is in V. Probability of the event x in V is also written like this, is the probability of the events that give this result V. And we can do it since x is a random variable and is a measurable function. And the last row here describes what I've told you. We take V, for example, this event, this concept. V is here the concept of greater than 3, and we look back and which events cause through the random variable have this output. and then we compute the probability of these events, these omegas. We compute the probability of the collection of omegas such that x of omega maps into the space V. So this probability measure on the random variable can be seen in backwards. So the probability here is equal to, right, I go to x, so to my V, and then I go back to the sample space and compute the probability on this. So we are evaluating the probability on the events, on elements on the sigma algebra of the sample space, referring to them through the random variable x. This gives us a lot of flexibility, since a random variable could be whatever we want, or how we can, the way we can describe a random phenomena through one or a set of random variables. For example, let's take this particular wheel of fortune from Wikipedia. In here, omega, our sample space, is 1, 2, and 3. We have different probabilities. And on the right side, you can see in this yellow set, in Wikipedia call it sigma, but it's our sample space, or better, the sigma algebra of the sample space. And to all these elements, these subsets, we can associate a probability. For example, here we can see the null set. We have no elements. Here we can see omega, that has probability 1. And then we have the other singleton or composite events. But the random variable, let's look at one random variable. A random variable could be discrete or continuous. And a random variable is discrete if the space in which it maps, it's finite or countable set of values, has a countable range. So the discrete probability distribution is called probability mass function, and is described like this. And here we can will write in this way, but remember that we are computing the probability on omega, on the elements of the sigma algebra in the sample space that the random variable maps to xy. If the random variable is continuous instead, we will use it's because the function maps to an interval or a collection of intervals, and we will describe the continuous probability distribution as a probability density function, f of x, also written as PDF, probability density function. Here we cannot describe the value of the random variable in a precise point like we do in discrete with the discrete random variables, but we have to take intervals. And to compute the integrals, again the circle is complete, we use the Lebesgue integral of the density function, the probability density function, on the interval. Let's see an example of a discrete random variable. For example, this is a particular distribution, a probability mass function for dice distribution. We roll 2 dice together, and that's the probability we can get. How many times we can get, we sum the result of the 2 dice, and we get this probability. How many times we can get the value of 2? 1 time, if we get 1 and 1. How many times we get the value of 3? Well, if the black dice takes the value of 1 and the white takes the value of 2, and vice versa, and so on. As you can see, we have a discrete number of values that the random variable can take, from 2 to 12. Another example of a discrete random variable is the one that has a Bernoulli distribution and could be seen as a coin flip. In fact, the sample space here is very simple. Can take values. The random variable can take a value 0 or 1. We write then to explicit the distribution of a random variable, we will use this symbol. So x as a distribution of Bernoulli, a Bernoulli distribution with parameter p. What is parameter p? Well, defines the probability of the event 1. The probability of x taking the value 1 is written as p. With a fair coin flip, p will be 50%, 0.5. And the probability of x equals to 0 is 1 minus p, also written as q. We can study another peculiar discrete random variable, which has the binomial distribution. We take now n coins. So we have n random variables, each of them having Bernoulli distribution with the same parameter p, the same distribution, the same probability for the event x equal to 1. And we perform what is called a Bernoulli trial. It means that we repeat independently n trials of the experiment with 2 possible events, which means that we are taking x as a Bernoulli distribution. So these x1, xn are independent random variables. We sum the results together and we get the so-called binomial distribution. This could happen also in the could happen if we take n coin flips and we sum the result head or cross. An example of binomial distribution here can be seen in this picture, in which we have several, in particular 3 binomial distribution. And this is the probability mass function, but we don't want to look at it in detail. You can study if you want, but for these slides is not that important. An example of continuous random variable is this type of variables. For example, here we are talking about a Maxwell distribution which is related to physics, but doesn't matter. As you can see, we don't have histograms, but continuous functions, and the color, the region is the area under the function itself. And here we have 3 continuous random variables. An example of continuous random variable is a Gaussian, also called normal distribution. In fact, if we take a binomial random variable as n, and we assume an infinite number of trials, and we will get that the Sn will become, we write x as a generic x variable, as a normal distribution with these two parameters that are also called, this will be mu, this term, and this will be sigma squared, this term here. This process of going from a discrete random variable to a continuous random variable can be seen in the Galton board. This is a flipping board in which we have several spheres in metal usually, and if you flip it, you can see that through a random process, the spheres will position to match almost this curve, which is the Gaussian distribution, the probability density function of the Gaussian distribution. Generally, also for simplicity of calculation, in nature random variables are usually described as continuous. Only if the phenomena is evidently discrete, then we will use discrete random variables. So we have seen so far the probability density function, the PDF. And we've seen that this probability density function, since this is a Lebesgue integral, must be a non-negative Lebesgue integrable function. But we can also define the cumulative distribution function, which is computed as a Lebesgue integral from minus infinity to x, which is x is our variable, and the function is the PDF. As you can see, this is a particular function that we already seen in the previous course when talking about the fundamental theorem of integral calculus. In fact, if for example, looking at the fundamental theorem of calculus, the first part, if the probability density function is continuous, then we can say that the PDF is equal to the derivative of the cumulative distribution function. So that's our relationship between the two. And the usage of one with respect to the two depends on that context. In the next course, for example, talking about a particular function, the risk function, we will use the cumulative distribution function, because some random variables could have the cumulative distribution function but not the density function. Another example of continuous random variable is the uniform random variable, which has a uniform probability density function. In fact, the probability here, the probability density function, is a constant and can be written as 1 divided by over b minus a. Here it is, our density function. The cumulative density function is its integral. It results in this one, and you can see that of course it matches to 1, since the maximum value of the probability is equal to 1. So goes from 0 to 1. Why? Since we say that f of x must be a constant, why we get that is equal to 1 over b minus a? Well, because the normalization property of the probability measure. So the probability on omega is equal to 0, which means that we have to compute the integral of a constant over dx, which results of the constant times b minus a. So 1 is equal to the constant times b minus a. So the constant is equal to 1 over b minus a. constant is equal to 1 over b minus a. That's it. From the probability distribution, we can extract some useful properties of the random variable, the continuous random variable or discrete random variable. For example, the first property is the expected value. What we expect, we could expect from this random variable, and can be written in this way. Let's look at, for example, at first at continuous. Is the integral over omega of x times the density function times the x. Is the integral of this product. Also, the continuous with a continuous random variable could be written as the integral of x over d, and we have a capital F, which means that we are integrating through the cumulative distribution function. But what the expected value is even more clear if x is discrete, and is equal to x times the probability of getting x as a result. So in practice, the expected value is just a probability weighted. Here is the probability, the weight, which is the probability of the event, that here can be described only by a density function. So the expected value is this probability weighted average of the values taken by the random variable. Another property that can be extracted from a random variable is the variance. And the variance is equal to the expected value, so the probability weighted average of the values taken by the random variable, but of what? Not of x, but of x minus the expected value of x to the power of 2. Also, this can be rewritten in this form, but let's start with this expression. This means that we take, let's look at the inside. We take the value of the random variables, and we computed the difference between the value and the expected value. Then we square the result, and then we compute the expected value, since x could be anything. This means that the variance represents how much the values of x are expected to diverge from the mean, and this sort of divergence is squared because the distance is squared. Let's compute the expected value and the variance, for example, in using a Bernoulli distribution. We remind that it's like a coin flip, and we have the probability of x equal to 0 is equal to 1 minus p. The probability of x equals to 1 of x equals 1 is equal to p. So here the expected value of x is equal to the sum. Here we don't have a series but just two terms, in which x could take value 0 or could take values 1. If x takes value 0, it means that here we get 0 times, which is the probability of x getting 0, 1 minus p, that's the term. And what about x equal to 1? Well, this is 1, and the probability of x equal to 1 is equal to p. So this multiplies, this 1 minus p multiplies by 0, so it's equal to 0, and we get that the expected value is equal to p. We can do the same with the variance, but now we have to remember that we have to compute the expected value of what? Of x minus the expected value of x to the power of 2. But we have already computed the expected value of x, which is p. so we can substitute and compute it right here. Now we have to do the same. We have this is 0 minus p to the power of 2, 1 minus p. Then we have 1 minus p squared times p. Rearranging, we get that this is equal to the variance of x is equal to p times q. Another property about the random variables is the Chebychev's inequality. And in particular, this Chebychev's inequality links together the expected value and the variance, or in particular its root, that is called standard deviation. And it says, let's look at, I think that the second expression here is even more clear. It means that the probability of x staying in this range is equal or greater than 1 minus 1 over k to the power of 2, which is k is a number that we choose. Okay, so it means that the greater k, let's look at on the right side. It means that the greater k is, the closer this value is to 1, since this term gets smaller and smaller. So we would like to see what it means with a k, with a big k. Well, let's see here. We get the interval. How is determined? Well, the random variable has to take values between mu, the expected value, minus k times the standard deviation, and mu plus k times the standard deviation. So of course, if k is big, it means that the range is wide. And the range is defined choosing mu and going k sigma to the left and k sigma to the right. Like this. We define mu, we go k sigma on the left and k sigma on the right. And what is inside here has a probability to happen that is equal or greater than 1 minus 1 over k squared. And this is a probability distribution. This is the curve. If we want to see, looking back to the previous, maybe we would like to see, okay, what's the range of what we wanted to know, how big k needs to be, since the white area is almost everything, let's say 99%. Here, looking at this table, we have to take 10 standard deviation to get the 99% of the points of the distribution to stay inside that range. For example, if we get the square root of 2, so k is the square root of 2, then we get only the 50% of the distribution inside of that range. Well, remember when we will talk about statistical inference, that we here mu and sigma are the true expected value and the true variance of the distribution, not the ones estimated from the data we collect. So these are the true values of that distribution. And we think we know, we suppose that we know those values. Typically, when dealing with data science projects or machine learning projects, we don't know about them. So another example of this Chebychev inequality can be applied with Gaussian or normal distributions. Here we write x, that as a normal distribution, with these two parameters, as I anticipated. The mu parameters, which is the mean, and the sigma squared is also the standard deviation here. That's a property of the Gaussian distribution that I will not prove here. As you can see on the right side, we can change mu, and what we change is the peak, the mean value, since the Gaussian distribution is symmetric with respect to the axis passing through mu. And the variance determines the distribution. For example, the yellow line here represents a distribution with a greater variance than, for example, the blue line. As you see, the peak and the distribution is not a lot dispersed around the mean, which is the peak here, the 0. But with the normal distribution, we get an even stronger conditions than the ones from the Chebychev inequality. Remember that we have seen that in the Chebychev inequality, to get the 99% of the distribution, we have to go at least 10 times the standard deviation far from the mean. Here, in the normal distribution, since it's this particular bell-shaped distribution, we have just to move 3 sigmas from the left and from the right of the mu, our expected value, to get the 99.73% of the distribution inside this range. And now I want to point out two other properties about random variables. And the first one is the weak. Here we talk about the weak. That's also a stronger version of the law of large numbers. In particular, I present this version. There are several ones. There's even one from Bernoulli. So let's consider n random variables, and this is a sequence of n random variables. There are independent and identically distributed, which means that we will see also later that independent means that the n variables are not related to each other, and identical distributed means that they all have the same distribution. So the distribution of x1 is equal to the distribution of xn. So, for example, a normal distribution, and their parameters are also the same, have the same values. So with these conditions, we have that the expected value of the generic, since they are identical distributed random variable, is identified as mu. And we also define this average, this mean, as the average of the values. This is a random variable because it is a linear, can be seen as a linear composition of combination of it's a linear combination of these random variables, and a linear combination of random variables is still a random variable, still a random phenomena. So the theorem is here, the law of large numbers says that the mean converges in probability to the mean, which means that if we take the limit of n to infinity, the probability of the mean, the distance between the average here and the expected value to be greater than a generic epsilon is equal to 0. So when we take an infinite sequence of identical independent and identical random variables with the same mean mu, then the mean, the average here at the limit will almost have the same value. That's the law of large numbers. But be aware that this sample average converges in probability towards the expected value, but means leaves open the possibility that this condition happens an infinite number of times, since there's an infinite number between 0 and n to infinity. Also could be at infrequent intervals. So yes, at for n that goes to infinity, this condition is true. So the probability of the sample average to be different than the expected value is equal to 0. But in the meantime, when approaching n to infinity, this could not also be true. So again, the law of large numbers, the weak law of large numbers, here states that when sample size tends to infinity, then the sample mean equals to the population mean. And here we have, for example, the when we flip a coin, we measure the excess of heads over tails in percentage. As you can see here, in the first 200 coin flips, we get important difference between what we expect. We would expect a 0% difference between heads over tails, and this difference goes to 0 as n, the number of coin flips, goes to infinity. The second theorem that I want to present you about probability is the central limit theorem, in which let's keep the sequence of n random variables independent and identically distributed. And now we say that the expected value is equal to mu, and the variance of the random variables are equal to is equal to this sigma squared. Then from probability properties, we know that the sample average has a mean mu, and the variance is sigma squared over n. The central limit theorem expresses that the sample average in distribution as a distribution as n goes to infinity, like a normal distribution. With here we are normalizing, and we are just saying that's an error here, it should be 1, but this means that we are normalizing the random variable, but we are just saying that this sample average as n approaches infinity will have will approach a normal distribution with mean mu and variance sigma squared over n. So the central limit theorem states that when sample size tends to infinity, the sample mean will be normally distributed. And here we can see, and please note that we didn't take an hypothesis on the distribution of the random variables x. But even not knowing this probability distribution, we know that the mean will have a Gaussian distribution with these parameters mu, and the standard deviation is sigma over the square root of n. So whatever the form of the population, the distribution of the population, the sampling distribution tends to a Gaussian, and its dispersion is given by the central limit theorem. Yeah, well, this is the dispersion, the standard deviation. But one phenomenon, and now we have to talk about one random variable, and we have expressed some properties about that random variable. But in practice, one phenomenon could be also explained using multiple random variables, and these random variables can interact with each other. For example, in this picture you can see a target practice explained through Gaussian normal variables. So we have here the x-axis, so the sniper has a blue distribution on the x-axis, and on the y-axis this red distribution. In 0, 0 we have the center of our target. Remember also that we have expressed that these multiple random variables can interact with each other. For example, if we have let's consider these two Gaussian distributions, that here we have x1 and x2, and the x1 expresses the distribution of the sniper to hit the target on the x-axis, and x2 talks about the y-axis. And for example, we express that the expected value of x1 and x2 is equal to 0. Okay, good. The sniper is good at his job, and the variance is equal to 1 for both of the random variables. But given these properties, the two random variables can be independent, so they are uncorrelated, they are not related to each other, or they can be correlated, they can depend one from the other. If the random variables are dependent, means that if the shooter, for example, shoots too far on the right, so shoots here, this is the center of the target, shoots on the right, then the arrow will likely also hit too high, because the probability of hitting on the right and high is greater, here we have the probability, is greater than here, that is almost equal to 0. That's some sort of correlation, or better, some dependence between x1 and x2. That's why we will talk about the joint probability. Here, the omega, the sample space of x1 could be 0. I hit the center of the target, the arrow goes east or west, and the same here for the center, north or south. So for example, if we want to compute that the arrow goes north-west, we describe the probability of these two joint events. and this is called joint probability between these two variables. We are saying, as the symbol means, the intersection between two events means this event and this event, so north-west. So this tuple is a multidimensional random variable and can be also described as a unique in the random variable, a multidimensional random variable, and has its own probability distribution, P of x1, x2. Since we get this joint distribution, how we can derive from the joint distribution the actual probabilities of x1 and x2? Well, we can do it through the marginal distribution. We say, for example, the probability of x1, what does it mean? It means that we have to compute the probability of x1 whatever is the value of x2. With a continuous random variable, we can do it with the Lebesgue integral. The same for x2, of course. Here, in fact, we are writing that the probability of x1 equal, for example, the value a, is equal to the probability of the event of x1 equal to a, and x1 equal to whatever element is the sample space of the x2. Then we can, I go very fast on this, then we can define the conditional probability as we have done for the events. And this conditional probability is written as the event west given the event north divided by the event north. We can also replace the same. That's it. Again, we can write the probability of x1 conditioned by x2 as the joint probability over the probability of the event which conditions the other. The two random variables are said to be independent if the joint distribution can be written as a product of the two marginals. Also, since they are independent, the condition probability equals the marginal probability here. We can also introduce the concept of correlations, and the correlations is determined through this function, the correlation function between x1 and x2. And we say that these two random variables are correlated to each other if the covariance of x1, x2 is different, is not equal from 0. And this covariance is computed as the expected value of x1 times x2 minus the expected value of x1 times the expected value of x2. It's easy to show that if two variables are independent, then they are also not correlated. Well, why? Because this expected value becomes the same on the right side here. But it's not true the vice versa. If the two random variables are correlated to each other, does not mean that they are linear independent. So if the covariance is equal to 0, it does not mean that the two random variables are independent. Why? Because we could study that the covariance is looking for linear dependence, a linear dependence between x1 and x2, such that x1 can be written as a linear combination of x2, for example. But that's not always true. the two random variables could be dependent with even more complex relationships that the covariance cannot catch. Also, if we have a n set of random variables, we can compute the covariance for each couple, and this becomes a variance-covariance matrix. Why variance? Because here the covariance of x1, x1, through this definition, is exactly the variance. So on the diagonal we have the variance, and since if we swap x1 and x2 we get the same result, it means that the variance-covariance matrix is symmetric between its diagonal. So this term, for example, is the same as this one. So the variance-covariance matrix is a positive semi-definite symmetric matrix. And some machine learning algorithms take advantage of these properties to diagonalize this matrix, simplify the matrix to catch even more properties that can be dispersed, that can be confused in such a mess, I would say, of information, an overload of information that is the covariance matrix. Also, since we have seen that the variance is a particular type of covariance, the Pearson invented the Pearson correlation coefficient, in which we compute the covariance over the standard deviation of x times the standard deviation of y. If the Pearson correlation coefficient, it means that the two variables are uncorrelated. In fact, the covariance is equal to 0. If we get that the coefficient is equal to -1 or +1, then, and this is these are the extreme values that this coefficient can take. This means that the relationship between x and y is linear, and the minus and plus determine only how this linear relation is expressed. And then we have the cases in between -1 and 0, and the 0 and +1. So that's it. We have described the probability. We have talked about a random variable, which is our tool to describe random phenomena. And then, looking at one random variable, we have studied the expected value, the variance, several theorems and properties and inequalities. And also we have took a look to what happens when we describe a phenomenon with multiple random variables, looking, for example, at the joint probability and at the independence of the variables, and at the correlation and the Pearson correlation coefficients.